Hello guys, in this lecture we are going to see the extrinsic semiconductors. In the last lecture we seen intrinsic semiconductors, and in this lecture we are going to see the extrinsic semiconductors. Electrical conductivity of pure semiconductors is primarily of electron type. The whole conductivity effect equivalent to a positive charge conductivity is comparatively weak. This makes the semiconductors exceptionally sensitive to the presence of any impurity. Most of the engineering applications of semiconductors involve semiconductors which have been doped intentionally with specific impurities rather than intrinsic materials. The drastic influence of an impurity on the conductivity of a semiconductor is a result of change in energy band spectrum. In case of silicon and germanium, the doping elements are either from third or fourth column of periodic table. The most frequently used elements from the third column are boron, gallium, indium, and aluminum. And from fourth column of periodic table, that are phosphorus, antimony, or arsenic. Addition of a fraction of a percent of such elements may increase the conductivity by several powers of 10. Also, the temperature dependence of conductivity is strongly affected by the impurity content. The semiconductors are of first is N-type semiconductors and another is P-type semiconductors. Let's see N-type semiconductor. N-type semiconductors are those in which silicon is doped with an element from the fifth column. For example, silicon with phosphorus, antimony, or arsenic. These impurities from the fifth column of periodic table have 5 electrons in its outer shell available for the interaction with the other atoms. Assume that small amount of phosphorus as an impurity is added to silicon, such as one phosphorus impurity atom per million atoms of silicon. Such impurity atoms are comparable in size to silicon atoms. Therefore, they can take positions normally occupied by silicon atoms. As shown in this figure, a conduction electron is shown here in this figure, which is of free electron. Because the impurity atoms are proportionality so few in number, each will ordinarily be entirely surrounded by silicon atoms. So in this structure, you can also see that these are the silicon atoms shown, and centrally doped atom, that is phosphorus, which is having the 5 free electrons in its outer shell. That in the last lecture we seen that the silicon to silicon having a covalent band with like that, it is getting a pair of the electrons. But here phosphorus having a 5 electrons in its outer orbit, and silicon having a 4. If you're getting a pair of phosphorus with the silicon, then here 1, 2, 3, 4, and fifth electron is remain as it is, which is nothing but free electron or conduction electron. The four nearest silicon atoms, you can see here near to the phosphorus atom. These are the four nearest silicon atoms. This 1, 2, 3, and 4. These are the nearest silicon atoms. Then it will form the covalent bond as I explained just now. These ties or these 4 electrons into the crystal structure with the forces that require a considerable amount of energy to disrupt. Obviously, you have to create a covalent bond here. So create this covalent or make the pair of the electron that requires the considerable amount of the energy. However, no such binding force holds the fifth valence electron. That's why it is keeping a separate as it is, or you can say here free conduction electron. In the energy band diagram, the energy level of this electron will be close to the conduction band, as indicated in this figure. This is the conduction band, and these are the electrons 1, 2, 3, 4, 5, 6, and 7, and these are the positively charged 1, 2, 3, 4, 5, 6. These are the extra allowable energy level associated with the pentavalent impurities. Pentavalent impurities means, yes, the atoms who are having a 5 free electrons in its outer orbit. For example, phosphorus. That's why it is called as pentavalent, and it is used as a doping element. So we are calling as a pentavalent impurity. Being almost free, it can be removed from the parent impurities atom by the expenditure of very little energy, that is Wi, only which is of 0.05 electron volt for silicon. In the contrast, it takes 1.12 electron volt to break this covalent bond. When free from its parent impurities atom, this fifth valence electron moves random through the crystal in the same manner as do the free electrons present in the intrinsic semiconductor. When an electric field is applied, there is a superimposed upon this random motion a steady drift towards the positive electrode that represents a flow of current. When the impurity atom lose an electron, it becomes a positively charged ion. Then the ion is immobile, therefore it is being bounded by 4 covalent bonds, and it cannot be contribute to the conduction of electricity. Impurity atoms like phosphorus that contribute free electrons as described just now, and that is called as donors because of they donate the electrons. In this example, we are considering the phosphorus and silicon. Here, phosphorus is called as the donor because that element is donating 1 electron. This is about the P type. Let's see the N type. We seen just now. We seen N type. Let's see the P type semiconductor. P type semiconductors are those semiconductors in which silicon is doped with the electron from the third column. For example, silicon doped with the boron, gallium, gallium, or aluminium. In this picture or structure shown, silicon is doping with boron. And I want to clear that earlier we seen the example of silicon and phosphorus, which is nothing but N-type semiconductor, and phosphorus was the donor. It was a donor element, donor, because it is donating electron, one electron to the silicon. That's why it is called as donor. And phosphorus having a 5 electrons in its outer orbit. It's very important. Now we are looking for the p-type semiconductors. In this p-type semiconductors, we are dealing with the boron and silicon, and boron is from the third column of the periodic table. Third column means obviously boron in outer orbit of the boron is having 3 electrons. That's why here we will see here what will happen. As in the pentavalent case, earlier case, these impurities atoms from the third column enter into the crystal structure and take place normally occupied by the silicon. In this figure, we can see simply silicon having 4 electrons in its orbit, outer orbit. So 1, 2, 3, and 4, and boron is having 3 electrons in its orbit. So 1, 2, 3. This remain as, which is called as hole. Which is called as hole. Okay. So 3 of these neighboring silicon atoms from covalent bonds with the 3 valence electrons of the boron atom. And although there is a natural tendency for each atom in the crystalline structure to form 4 covalent bonds. Obviously, I'm sure just now I shown that 4 covalent bonds, and the trivalent boron atom is short of 1 electron. Obviously, boron having 3 electrons in its outer shell, outer orbit. So that's why there is short of 1 electron for to creating the covalent bond. As a result, it seeks to acquire a 4th electron, and it does and it does this by taking advantage of any thermal motion that fortuitously bring an electron from a neighboring silicon atom into the favorable condition to be captured. Such capture is very small, and it requires the energy of 0.08 electron volt in case of silicon. When this happens, the impurities atom boron establishes covalent bonds to the 4 nearest silicon atoms. It then becomes an immobile negative ion embedded in the crystalline structure. In this energy band also you can see this is a valence band and this is conduction band, and this shows valence band having positively charged holes, and these are the electrons having an extra allowable energy associated with the trivalent impurities. Trivalent means 3 electrons, the atoms who are having a 3 electrons in its outer orbit. Okay. The act of stealing an electron from the silicon by an impurity atom produces a hole that is similar to the holes arising from the breaking of covalent bonds. This hole moves about in random way due to the thermal effect, and when an electric field is applied, it tends to drift towards the negative electrons, and this contribute to the flow of current. Obviously, the impurity atoms that contribute the holes in this manner are termed as acceptors. Termed as acceptors because they accept the electrons from silicon atom. As we seen in the N type, phosphorus is nothing but a donor phosphorus atom, and here boron atom is called as acceptor. It because it accepting the electrons from the silicon. The electron and optical properties of the semiconductor materials are strongly affected by the impurities, which may be added in precisely controlled amounts. Such impurities are used to vary the conductivities of semiconductors over wide range, and even to alter the nature of conduction process from conduction by the negative charge carriers to positive charge carriers. This is about the p-type semiconductors. Let's see the Hall effect of semiconductors. Hall effect. How can we determine whether a semiconductor is N type or P type? It is very important and the valuable question. They look like, and a simple measurement of resistance will not distinguish the semiconductor material as a N type or P type. To our rescue or overcome the Hall comes to the Hall effect, it will rescue from this question. So a phenomena exhibited by conductions carrying current when placed in the magnetic field. When a transverse magnetic field is applied to a conductor carrying current, under this condition, it is found that in addition to the longitudinal electric field normally present, a transverse field is produced that is perpendicular to both the direction of electric current and the applied magnetic field, so that the current and the electric field are no longer parallel. The effect thus produces a measurable transverse voltage across the specimen. The Hall effect has played a decisive role in relieving the mechanism of conduction in the semiconductors. The conductivity of a semiconductor does not determine the mobility and the density of charge carriers separately. However, in case there is only one type of charge carriers, the density of charge carriers can be found from the measurement of the so-called, it is called as a Hall coefficient, and it is indicating with the capital R in the suffix with the H. Hall coefficient of the material. Let us discuss the Hall effect for p-type material. Assuming the carriers to be positive holes of the charge E. In this figure shows a slab of p-type material in which a current density J results from an applied electric field Ex. Applied electric field Ex. Here you can see here, due to the applied electric field Ex, here the current density appears as a J in this diagram. Due to the presence of Ex, the carriers assumed to be holes will drift with the average drift velocity. That is, that drift velocity is nothing but Vx. X for the drift velocity in the direction of x. That's why it is written as a Vx. When a magnetic field of flux density Bz, here you can see magnetic field is applied to this slab also. So in the direction of Z here, Z. That's why it is indicating with the Bz. Then it will experience a Lorentz force perpendicular to the Vx and Bz. Perpendicular to Vx and Bz. This is well known as left hand rule or motor rule for the force exerted by the negative y-axis, and that force exerting on that slab by the magnetic field on current carrying conductor, or you can say current carrying slab. The magnitude of this force can be calculated or can be given as per the fundamentals, that is E into Vx into Bz. This is nothing but the force exerted on this slab, that is E into Vx into Bz. Obviously, that is E is nothing but uh, charge E, and Vx drift velocity in the direction of x, and magnetic field is applied on the slab in the direction of z, that is flux density in the direction of z. Due to the presence of this force, positive carriers are driven towards the front face. For example, you can see here this front face appearing with the positive charge, which is shown in this figure, and resulting in excess of holes near the front face, and a deficiency of holes are the back face. Deficiency of the holes means obviously on this back side the negative charge is appearing here on the back side of that slab. To have equilibrium, the Lorentz force in the direction of negative y, is just compensated by the force produced by an electric field Ey along the axis of y. So it can be write as the equilibrium force. According to the equilibrium force, the E into Ey, that is force acted due to the electric field Ey in the direction of y. That's why it is written as, this force is written as E into Ey. The same force is appearing on the slab due to the Lorentz or left hand rule, according to the left hand rule. So it is equilibrium, or comparing these two forces, that is E into Ey is equals to E into Vx into Bz. So it can be appear as a Vx, that is drift velocity in the direction of x, can be evaluated as Ey divided by Bz. Also, the current density in the same sample given by the Jx is equals to Nh into E into Vx, where Jx is the current density in the direction of x, and Nh is the density of holes, only considering the positive charge here. Now, by substituting the values of Vx here, Ey upon Ebz here appearing, if you are substituting the value of Vx into this equation, then we can calculate from these above three equations. We can calculate the Hall coefficient, that is indicating with the RH, and it can be written as RH is equal to Ey divided by Bz into Jx is equal to 1 upon E into Nh, and also it can be written as minus 1 upon E into Ne. Here you can differ with the Nh and Ne. Nh here NH is appearing on the front side. That's why it is considering for the holes it is considering positive value, that is 1 upon EH, and electrons appearing on the back side, so that's why it is considering in the negative direction, that is minus 1 upon E into Ne. This is about the Hall effect, and the last equation gives the NH provides. We know that if we know Ey, Bz, and Jx, we can go for the calculation of Hall coefficients. This is the whole about the Hall effect. So thank you for listening to me. Thank you very much.